Well, thanks everyone for coming to this seminar talk today, both in person and online. So my name is Chen. I'm an associate professor at Chen School of Engineering, working on robotics and computer vision. And I got to know Wuyang a couple of years ago. So our speaker today, Wuyang Chen, is an assistant professor at Simon Fraser University. Recently joined there and just started his career there. He has been, he got his PhD from ECE at UT Austin, and then postdoc at Berkeley, I believe, before he joined the SFU. So today he's going to, well, he already have, he's definitely a rising star in this field and have many good works in different AI and machine learning conferences, top venues. And so today he is going to share with us his work about a very interesting topic on PDE and LLM. So without further ado, Wuyang, it's your stage.
Yeah. Thank you, Professor Feng. So very kind introduction, and I really appreciate this chance for us to introduce our latest work. So as Professor Feng just introduced, that I'm Wuyang. I'm currently a new assistant professor from Simon Fraser University. So it's in Vancouver. So perhaps you know that nowadays many machine learning conferences are happening in Vancouver. So if you have chance to attend these conferences, feel free to drop by our campus. So today I'm going to share our latest work called the PDE-Controller. So the high level idea is that we want to leverage language models to do some auto-formalization and reasoning on PDE control problems. And just like this icon shows that essentially we want to control the behavior of these PDE equations by applying some external control signal. It's a joint collaboration between my students and some of my colleagues in the math department in SFU and some language model experts from Princeton. All right. So the high-level background of this project is a very important research direction that recently arises, which is AI for math, or more specifically about leveraging language models to solve pure math problems. So some examples like geometry, probability, calculus, etc. And these works try to solve problems with difficulties range from grade school math to Olympic challenges. And some of them, especially for theorem proving problems, people try to interact language models with theorem provers, such as LIM. So some hot news you might heard of is that Google DeepMind developed this alpha geometry several versions, and they won silver, and I think this year they even won the gold medal. So quite impressive breakthroughs. However, when we took a look at the global picture, we know that the pure math, the problems I just mentioned in the last slide, mostly about pure math, but we know that there are a whole bunch of problems that actually belong to the applied math. Some typical examples like the PDEs, partial differential equations, or the optimization. So from my personal perspective is that I think these problems are equivalently important with the pure math problem, but in contrast, they have more closely related to real world problems. Actually, I saw one.
I'm just telling the
okay.
online if they have questions.
Sure. Okay. However, comparing the works that have been done for the pure math problems, I think people lack both well-defined problems and data sets to apply language models for applied math problems. So in this work, we specifically focus on the PDE problems, where PDE is mostly used to model physics systems, like essentially some properties in the system, like the temperature or the force, or some dynamics about the system. And especially when we want to control the properties of the systems, usually we can achieve this by controlling some external factors, external variables in these PDEs, and then we can control this system. So just some example. I saw another message. Questions or? How to record and share this coding? I think sure. Yeah.
Yeah,
Okay.
you don't need to worry about
Okay,
that. I'm
okay,
going to remind
Oh,
you.
okay, yeah, sure. Sure, thanks. So just some examples on the PDE control problems that we target. So for example, consider a 1D spatial domain, and we can apply a heat source, external heat source. So usually the requirements for these problems looks like we want the temperature between x1 and x2 to fall between 300 plus minus 30. So to achieve this, so definitely this will be a dynamic distribution of the temperature along this spatial. So to achieve this, we can apply an external heat source so that we can control the energy that can be input into the system and then control the distribution of the temperature. And on the other side, if we replace the heat source and external force term, then we can control the displacement of each position in this material, so that we can so each position can be either be stretched or compressed along the spatial temporal dimensions. Just an example of the final state and the solutions. So for example, in this plot, it's the state of the system at a certain timestamp. So the x-axis is the spatial location, y-axis is the temperature facing the system state at this timestamp. And the solid black curve means the temperature distribution, and the three colorful bars are representing the constraints we want to meet. So, for example, this blue and red bars means that at this timestamp, we want the temperature to be above these two bars, so that we can have some positive utilities. And the bottom plot shows the solution we find, basically the solution of the heat source to be applied to the system. So we can see that the heat source, so the unit is the, I think is the milliwatt, and the y-axis is the seconds. So we can see that the power of the heat source will change along the spatial, along the temporal dimension. So that means we want to control the distribution of the temperature of the system by controlling this external source. Here is the heat source. So traditionally, how people solve this problem, we want to give a brief introduction. So first, we still need human to define the problem. So for example, scientists and engineers want to define what kind of PDEs we want to control, either the heat equations or wave equations or some other more advanced equations. And then we need to define the specifications, basically those constraints we want to meet for this material, for this system. So we always need the human to define the original problem. And then human need to formalize this problem into a constraint optimization problem, and then run some external optimization solver to solve this problem. So this is a traditional approach. However, we can see that first, the first step is always true, because the human is the ground truth here. So we need to serve with human, whatever human engineers, scientists they care about. But for each problem, human need to spend their own time to manually rewrite the informal problems, informal definitions into a formalized constraint problems. So this needs time. And especially if we have lots of constraints, like 3 or 4 or more constraints, and if they are conflicting to each other, then this formalization will take a lot of time, and human could make some mistakes. And also, to actually run the external solver, to run the simulations, people need to run the code and write the code, and people may make some bugs. So this whole three steps by traditional approach will introduce actual human efforts and may introduce some errors that people may not be able to find easily. So in our project, we want to see if the language model can help us in this problem. So two core questions we ask. So first is that, can language model help us to solve this PDE control problem? So that's a very basic problem we want to ask. And the second question is that, which is more advanced than the first question, is that suppose we can find that actually language model can help us do this. I think a more interesting question is that, can language model do this better than human? Can language model solve this problem better than when we humans spend our own time to solve it? So that means, can language model can do some reasonings or plannings with some so-called common sense, or more specifically scientific common sense, better solve this PDE control problem. So I think that's the second and the more important question we want to solve. All right, so back to our traditional methods, what we want to replace, right? So first we want to replace the second part where human used to formalize the problems manually. So we first want to replace it by language model autoformalization so that people don't have to intervene this problem and just let the model to do the formalization. And third part is that previously human need to write code and call the external server. We want the language model to automatically write the code, and hopefully this code can be bug-free and successfully run the code and achieve the desired results. And more importantly, to answer the second question, we want to see if the language model can do some plannings so that it can achieve better performance, better control utility than human can do. So that's the whole pipeline. That's scientists define the problem, and we use the language model to formalize the problem into formal specifications and write the code and hopefully do some reasonings to better solve this problem. All right, so this will be a quick overview of our framework. So after I discuss specific parts, we will go back to the overview. So right now you don't have to memorize anything. So I will just give a very quick impression. So originally we have the data that will include both the informal language, language to define the problems that introduce instructions, basically what we want the language to do, and the core problems. And then we have the auto-formalization. We will train a language model called the translator to formalize the informal problems into formal languages, which are where we use the signal temporal logic to represent the constraints. Basically, it's a logic combined with multiple sub-constraints together. And then we have the coder to ask the language model to write Python code, which can further call the external server, such as Groovy, to run the numerical simulations. So if we only have the auto-formalization and the program synthesis, the whole system can still works. You can just naively translate the original problem and run the code and solve the problem. Basically, start from the initial condition of the PDE and then directly solve until the end of the control. So everything can work perfectly. However, as I mentioned, that we want to achieve something further. So we train another language model called the controller. So if we start using this controller, we will introduce another reasoning step. So right now, the whole step will not directly be solved from the initial condition to the final state. But we will first try to solve the reasoning step from the initial condition and reach an intermediate system state. And start from this new state, we will roll back to control the original problem. And hopefully, by adding this reasoning step, we can achieve this control problem to have better utilities. So that is the core motivation where we introduce this controller. So just a reminder that without this controller, everything still works, but just naively. But we want to add this controller to hopefully achieve something better. All right, so we will step introduce these two parts. So first is for the auto-formalization and program synthesis. So we will first introduce what our data looks like. So we have, so basically it's an informal language that define the problem. So for the instruction, it's quite straightforward that, for example, we tell the language model that below is a natural language description of a PDE control problem, and we want them to translate the problem into the tag code with the STL formal language. And for the target problem, it's usually include two parts. First part is about the constraints. So basically, we want the temperature to follow this profile, this style. And this constraint need to be satisfied within a certain spatial domain and the also the temporal domain, 4 to 5 seconds. And we could have multiple constraints like the second one. So essentially, we need to ask the language model to combine multiple constraints properly with binary operators. And also we have some system descriptions, basically to tell us the dimension of the spatial domain and some initial conditions and what kind of PDEs we want to solve. And our translator language model will extract the constraints from this informal language and then formalize it into a formal language written in the tag code. Basically, will represent the STL, the signal temporal logic. So basically, it's the tag that represents multiple binary constraints. Say we want the temperature of the system to meet these requirements within certain spatial dimension, and we will connect multiple constraints together with these binary operators. And after this translator language model formalize this problem, we will train another code, so-called the coder language model, to help us write the code. So basically, this code will be able to call the Groovy optimization solver, but inside the coder, we need to extract these initial conditions and also insert these formalized constraints properly into this whole bunch of code. And hopefully, if this code is bug-free, then it can call the external solver to solve this PDE constraint optimization problem, and then we can get the final utility and the solution for the external source. So you can see that essentially to solve this problem, we still need external solvers like the optimization solver. But the key aspects, key role that the language model will play is to take the could be noisy and informal human written problems into formal languages and also help us to write code. And then the language model will interact with the external solver to essentially solve this problem. And a quick overview of how we design our data. So this paper is a end-to-end solution. So we build our models. We also build our data set because this is a completely new data set. No one proposed this before. And we also have our evaluation metrics. So the whole project is very new. So we build the whole system from scratch and train the model from scratch. So basically, we iterate different types of the STL syntax. And also we support different number of constraints, like 1, 2, 3 different constraints. We didn't consider more because that will require us to generate much more data. So we didn't have time to do that. And we connect different constraints with different binary operators. And to further augment the diversity of the data set, we use GPT to further augment the trivial parts of the problem so that our data set could be much more diverse. And then we sample the hyperparameters, which defines the specific problems like the initial conditions, the spatial temporal domain range for the constraints, and the detailed constraints itself. So the samplings will define lots of different problems. And essentially, we collect over 2 million samples, and we believe that this over 2 million samples should be enough to perform the supervised fine-tuning training. And we have different samples for heat problems and weight problems. So we mainly consider these two types of PDEs and for different number of constraints.
Here's a question.
Yeah.
What do you mean by a sample?
Sample.
Yeah.
Sample. Yeah.
So a sample is somebody describing a PDE
Yeah.
problem?
So
there are 2 million people describing PDE problems?
So first is that for this data set, like 2 million samples, it's kind of synthetic data set. We have rules and code to automatically generate this bunch of problems. So it's for this part, the 2 million samples, they are not written by human. So we human write some seed problems and we further augment these problems.
How many seed problems?
Yeah. So seed problems is that 6. If we only have one constraint in the 6, and we have 1, 2, 3 different combinations. So I think these are seed problems. Basically, they are templates. And so these third and fourth steps are different ways to enlarge the whole data set to increase more diversity in this data set. So to give one example, so this part is one concrete example of the problems, which defines the one constraints and different temporal and spatial domain and the some initial conditions. So basically, so here in this problem we have 2 constraints, but we may have either 1 or 3 constraints. And these constraints can be either connected by or and operators. So we'll add another diversity.
But the specific numbers like 30 and 60,
they're random. They're random. And especially this randomized sampling actually will lead to very different solutions. So even they could be trivially different by a few numbers, but their solution could be very, very different. Yeah, and some problems may even not be solvable.
For example, if 30 is bigger than 60.
Yeah. That's true. Yeah, that's true.
But those simple things do you do a filtering to remove those? that
No,
are
no,
naive?
no. So
Just add.
we just so among these 2 million samples, there might be
There's no sanity check.
uh so they are always valid. So the problem itself are valid, but we don't guarantee
Could be trivial.
they could be trivial or they could be infeasible.
Okay.
It is all possible.
I have a follow-up question. I think this is a great question.
Mhm.
So what are the other things that you vary when you generate those samples? Is it just these parameters, or will the language, because the natural language description itself could
Yes.
vary.
Yes.
It doesn't always follow the same like a sequence of order of
Yeah.
description. It could be everything, right? Do
Yeah.
you use some like post-processing
Yeah.
to make them more diverse?
Yeah, that's a very good question. So first, in this part of synthetic data set, we consider some of the language level augmentation. So yeah, and for the second part, where the whole structure could be changed, that's a very good question. That's why we also include real human written problems. So we conduct several Zoom sessions to recruit some graduate students. Yeah. We even have that. Yeah, so I will include that part. All right, so for these 2 million samples, there could be some trivial problems, infeasible problems, but we include all of them.
Sorry, and one quick question.
Yeah.
So there's no constraint for you to generate even more. I guess this.
Yeah, definitely. Just a time limits or yeah. That's true. Yeah.
So curiosity, what would happen if somebody says, I want you to tell me the initial condition, so that the final temperature is 2 in some range and 3 in some other range. The point about that is that it's a nil-post problem, and if you try to solve it, if you discretize it, it's not infeasible, I guess, but from a physical point of view, it makes no sense.
Right. So essentially, we have ways to quantify whether the final solution is actually solving this problem or not. So we have a way to even tell us if it can be solved, then is how better it is solved. Yeah, we have
write a code, run a code, look at the results, and say this sucks.
Yeah. Exactly. Yes.
Perfect.
All right, so this is a data set, and okay, here is the human data we collect. So as I just mentioned, that actually we will find that the human written data actually looks quite different from the synthetic generated data. So it's important for us to verify how the language model will behave on some really noisy real world data. So we recruit either graduate students or undergrad students with different, I think, highly relevant backgrounds to help us write this code. So what we did is that we give some examples to human participants, and we set up a one-hour Zoom session to instruct them to how they rewrite their own problems. And after that, we find that there are actually some very different behaviors of these human written problems. Like people made some symbolic mistakes, like some typos, which will always confuse the language model. And there are some inconsistent units used by humans within a single sentence. Like sometimes they switch from the seconds to milliseconds just in a second in one sentence. So it can confuse the language model. And also there might be some insufficient information that, for example, a human may forget to add some like the initial conditions, or human can restructure the whole paragraph. So this kind of noise will actually hurt the language model performance, as I will show later.
Do you have to define those symbols in the natural language description?
Yes, we need to tell the language model that this you need to represent this number with a symbol.
Okay, so in the description there is a constraint that you have to.
So actually in this sample we I think like C underscore B. Basically we tell the participant that you need to give the variable a name.
I see.
Yeah,
I see.
and hopefully the language model can know that when he writes the code, he needs to use his name.
Got it.
Yeah.
There's a question from Ankit
Yeah.
Bardwedge online that he wants to know first whether the heat and wave equations in the dataset are all one-dimensional.
Yeah, they are spatially they are one dimension.
Spatially all
Yeah.
And then I guess another question, you probably will talk about it, like whether the system generalized to other PDEs.
That's an interesting question. The quick answer is that in this project we didn't, but we really want to look into more advanced PDEs or generalize to more multiple dimensions. Yeah. All right. So there are some discrepancies between synthetic dataset and manual dataset. Okay, to train our model for this formalization and program synthesis part is quite straightforward because in our dataset we have paired informal language and the formal language and code. So we can just use the supervised fine-tuning to train our model to do the formalization. So they are just cross-entropy laws given the natural language to formalize into the formal language. And given the natural language and the formal language, predicted formal language, we ask the language to generate code. So these are quite straightforward. Another important part that's why we want to do the reasoning, right? Before that, we only have the formalization, but as I just mentioned before, that we want to achieve something further than the formalization, so which is the reasoning part. Before I introduce the reasoning part, an important part is that why we want to do the reasoning or why reasoning is possible on PDE control problems. So I need to introduce this motivation. So first, what does reasoning mean in PDE control problem? So one motivation is that the PDE control problem is a non-convex problem. And since it's a non-convex problem, that means that any solver could make some mistakes and there are always some rooms to, perhaps we have some rooms to improve the non-convex optimization. So why this PDE control is non-convex? So this is rooted in how we quantify the utility of this PDE control. So when I say utilities, that means whether this solution actually satisfies our constraints or if it satisfies how well it satisfies. So for example, if we have a constraint like this, we want the temperature to be above this AX plus B, then the utility will be the temperature minus the constraints. On the other side, if we want the temperature to be below this constraint, then we need to swap. And if we have multiple constraints connected by some binary operators, then given depends on different operators, we use we find the minimum or the maximum of these two utilities. And there are some more advanced requirements on the constraints. So that will also introduce different ways to calculate the utility. So as you can see that since we have the min and max and different operators, so clearly this object function itself is non-convex. So that makes this PDE control problem itself is non-convex. After the discretization, this problem can be formalized into a MIP problem, the mixture of integer linear programming problem. So since it's a non-convex problem, so that means there might be some challenging optimization landscape in the whole process. And perhaps there are some barriers or values that stop us from better solve this problem. So we want to know that if we can, beyond naively solving this problem, can we actually find some intermediate step that can help us avoid these barriers or values in this optimization landscape so that we can solve this problem better. So actually this motivation is inspired or quite similar to where people use language model to control the robots. For example, if we want the robots to start from the beginning to some ultimate goal, and if there are some obstacles in between the starting point and end point, hopefully we want the language model to help the robot to avoid these obstacles. So similar here that if we find the optimization problem is hard to solve or there are some room to improve, then we hope that we can find some intermediate step to help us achieve the better utility. Right, so then after introducing these motivations, here is how we achieve that. As I mentioned that we want to find some intermediate state to help us solve this non-convex optimization better. So we want to train a language model to propose some intermediate control steps. By solving these intermediate steps, then hopefully we can get better utility. So first, given the original problem, like the instruction and problem, the controller will propose a sub-goal STL proposal as an intermediate state. So originally, we start from the initialization, and this phi represents the original constraints. And by directly solving this constraint, we reach the final state and we have the utility. And now we have the controller to propose some sub-goal STL as a 5 parameter. So in this reasoning step, we will first try to solve from the initial condition and try to solve this 5 parameter. So this is a complete new problem and reach an intermediate step. And we will start from this intermediate system state to roll back to solve the original problem and get the new utility, which is the utility of the 5 given the 5 parameter. So one remark here is that we actually don't care whether this intermediate state is solvable or not, because all we want is a new system state. And hopefully this new system state, this new initial condition can help us get a new utility. And to solve this, we need to use the reinforcement learning to train the language model, because right now there is no such a ground truth or rule of thumb for this 5 parameter. So there could be lots of different ways to propose this new 5 parameter and give us better utility. So there's no ground truth or correct answer for this. So there are only better answer or worse answer. So the way we train this model is that we prepare this preference data. So this preference data is each sample is a pair of 5 parameter. So we denote it as 5 parameter winner or 5 parameter loser. So the 5 parameter winner means that if we insert this 5 parameter to the system, we can get a better utility than directly solving this problem. The 5 parameter loser means that this loser constraints will actually lead to worse utility. And we use reinforcement learning to shift the language model's distribution towards these winner solutions and push away the language model distribution further away from this loser constraints. So after this reinforcement learning training, basically we use the DPO, the direct preference optimization, such that after this fine-tuning, language model can more prefer to generate the distribution of the response similar to distribution defined by this winner solution, but will be very far away from this loser solutions. So that means after this reinforcement learning fine-tuning, during the testing, given an unseen problems, hopefully our language model can roughly know that how to map this original problem into a very different constraints. And this constraint could be more likely to give us better utility. So that's how we define this PDE-Controller reasoning and how we build new data set and then train the language model.
How effective generate those
Right.
10,000?
Right, that's a good question. So to build this preference data set, we use random sampling. So remember that in these constraints, it has lots of sub-constraints, right? There are some hyperparameters define this constraint. So we randomly perturb these constraints, like spatial temporal dimension and the coefficients of the linear constraints. And there might be some perturbations that give us better performance and some worse. So we pair them together. Yeah.
But I guess still, like, how long does it take to?
Oh, yeah. I think my student take like 3 days, 4 days.
And these are experts. They need to know these problems. They need to solve this problem.
I definitely would like to call my student experts.
Right?
Yeah. But I mean, they don't have to be PDE experts, to be honest. So the whole
Right, these are not people you can hire from Amazon Mechanic Turk to.
Yeah, perhaps. So they at least they need to understand which good domain to preserve. Yeah.
Like at least undergrad students who have learned PDE.
Yes, they have some background on this. So yeah.
So how scalable do you think this kind of RLHF apply to this domain? Like, will we and considering the overarching goal that we're trying to achieve?
Right. I think at least one aspect I can try to explain is that actually before we finish these experiments, I think at least to me that it's highly unpredictable if this problem can be solved. So I'm to be honest, I'm highly uncertain because I think this problem is highly non-trivial. That how to find this 5 prime, right? I think for any similar problems, whether we can use a language model to do this is highly dependent on the difficulty of the problem itself or the room that can be improved. So actually, I have some relevant results I can show later that if the problem itself, if the non-convex problem itself is highly complicated and there is not much room to improve, then I think either to build that data set or use reinforcement learning to train the language model will be very difficult. So basically, the language model can hardly find a better solution. But if the solver itself is very bad, or the algorithm to solve the non-convex problem is very, very bad. So that means this bad algorithm can give us a lot of room to improve. Then I think the language model can do some job here. So I think it highly depends on the difficulty of the problem itself.
There's a question.
Yeah, sure.
So, from Ray-Xuan, what does the reward function look like?
Oh yeah. You mean the utility score or the reward? So the reward or the the reward itself is the PDE-Controller utility. So basically, here's how we control utility. So the positive value means that the final solution already meet the constraints. The negative utility means that this problem is not.
Have the ground truth.
We have the ground truth. We do the simulation. Yes. And this is a loss function for the reinforcement learning. So so actually, when we train the language model with reinforcement learning, we don't directly use the numerical value of these utilities, but we use the numerical value of the utility to tell us which is the winner, which is the loser.
So basically, when you generate, okay, in that synthetic 2 million samples, of course, you get the ground truth.
We have the ground truth, and we further pair those 2 million samples into these pairs. So these pairs are rooted from those 2 million samples. So
what about the manual?
Oh, so the manual so for the manual we don't have this pair sample because we need this preference data to because we need to train the model, but to evaluate the model we don't need this preference data, because to evaluate all we need to do is that we first run the ground truth solution, and then we run the language models proposal so that we can compare. All right, so I will continue. All right, so this whole method part, I think I can go back to show our framework again. So just a reminder that we have data, formalization, coder, and we have different states, and hopefully we use a controller to control this problem to get better performance. All right, so then we move to the result part. So first we want to evaluate the formalization and the program synthesis. So we introduce multiple metrics to evaluate the quality of the translator and the coder. So we don't have to go into the details, but the high-level idea is that we need multiple different granularity of metrics to probe the quality of the autoformalization and the program synthesis. So for basically, we want to decouple the evaluation of these two language models. So for example, for the constraint itself, which is formalized by our translator, we will use the intersection of union to quantify how well the predicted constraints align with the ground truth constraints. So if the IOU is very high, that means the language model successfully extract the constraints from the informal language. And for the program synthesis, well, we have two parts. First, they call the utility, the executability, and the other one is the utility RMSE. So we do need these two metrics because the utility can only the executability only tell us if the code is bug-free. But being bug-free is not enough. So the code can trivially be written like return 0. So this is always bug-free, but the return will always be wrong, right? So the executability can only tell us if the code is runnable. But we do need the utility RMSE to compare the simulation result with the ground truth so that we know that if the generated code can faithfully solve this problem. So we compare our language model with different either open source or closed source language models on these two problems. like the mass coder is an open source language model. The GPT-4 or 1 million are open code source. We have to use their APIs to solve the problem. So and these three models are evaluated with few short learning. So basically they are not fine-tuned, but we provide some examples to allow them to do the in-context learning. And this IOU, executability and utility RMSE are different aspects to quantify these two language models, the translator and the coder. So in general, we can see that on this synthetic data set, our translator and the coder can achieve much better performance than these in-context learning language models.
So the 50.58 means that that's a fraction of the codes. It didn't raise syntax errors when they were.
You mean like this?
Yeah.
Yeah. So this part means that among all the generated codes, there are only 58 of them actually runnable without bug.
So bug means syntax error. It doesn't mean bug in the traditional sense.
Bug means that
Like off by one errors might run, but it'd be wrong.
Yeah, that's true. Basically, the compiler will raise some errors.
Right. Okay. I teach this stuff, and when students use ChatGPT to write code to solve a numerical problem, it never works.
Okay. All right. Yeah, I mean, these GPT models are actually
They end it in, and it's always wrong.
Right. So I think if we are not focusing on this domain specific problem, I think in general GPT models are very strong on in writing code. But I think this is a very domain specific problem. I think they may made some mistakes.
So what do you think is the main reason of the performance difference between yours versus the other three baselines?
I think basically we are fine-tuned on this problem. So this level really solve this problem.
I see. So those like the mass coder too, none of these are fine-tuned on your data.
So at least they have some basic knowledge. So the mass coder can itself can generate the tag and Python code. Yeah, but it's
not
never
specific to
this problem. Yeah.
PD problem.
Yeah. That's true.
And they don't have access to your 2 million sample.
Of course. But it's very hard to make a very apple to apple comparison. But at least for these GPT models, they are much larger than ours. We are just 7 million models. Yeah, so it's kind of a trade off. All right. And now it's the human written data. So now we can see that when we switch to, we have 17 human written heat problems and 17 human written weight problems.
Sorry, there's a good question. So also from Anthill, what is the RMSE for traditional methods done by experts? Like the human baseline for these problems.
All right. That's a good question. We didn't test that. I think one reason we didn't test it that definitely we don't. I don't want to ask my student to do that. That is unfair, right?
How large is the testing?
For this human written data, we have 17 heat and 17 wave. But even to write the problem, it takes us several hours to instruct the participant to do that. I think if we let the participant students to write the code, I think that will take awfully too much time. So we didn't.
For these 17.
I think so, because some of them didn't use Groovy. So yeah.
But I thought that actually may be important to help people understand the RMSE number. Are they good enough?
That's true. That's true. Yeah, I think that's a good question. I don't have definitely I don't have an answer to that. I mean, if I ask my students to write it, I think this performance will be very high.
So high.
Yeah, I think that's different ways to interpret this table. So in this table, these three columns are fully decoupled. So the IOU can basically tell us the quality of the translator. The executability itself is evaluated with ground truth IOU. And utility is also evaluated with the ground truth IOU. So it might you might see that for example the error from mass coder or the some people very much small, but their translator is very bad. So if we evaluate them end to end, so essentially their performance will be bad.
So basically, you excluded those non-valid.
Yes, exactly, to make some fair comparisons. But still, in general, on very noisy human written data, the performance will drop significantly. So I think so that tells us it's important to in the future we need to generate more diverse data set. Yeah. All right, so this is for the formalization and program synthesis without any reasoning part. Okay, so now is the result for the reasoning part. So we need new evaluation metrics. So basically, we want to quantify how successful the intermediate proposals are. And we have two ways to quantify. First is the successful rate. So that means if we ask the model to generate multiple times, then how much successful rate can the language model to find some good reasoning steps. And this success rate doesn't consider the absolute utility gain. So how much utility gain can we achieve? So if we further consider the utility gain, that means we take the expectation over the generated intermediate state. So basically, there are just two perspectives on quantifying how good the intermediate steps are. And so this is a question that might answer Professor Feng's question that on different problems, how feasible the language model could achieve. So to answer this question, we split our reasoning data into 3 difficulty levels, easy, medium, hard. The way we make this partition is that by the random sampling. So if a problem after some random perturbation can easily find winner solutions, that means this problem are very easy. So basically, this problem have a very large room to improve. But for hard problems, that means no matter how many random perturbations we do, it's very hard to find a good reasoning steps. So basically, this hard problem means that these problems don't have any enough room to be improved. And we try to make our reasoning data to equally distribute among these 3 difficulty levels. All right, so final result for the reasoning part. So we have heat problems, wave problems across difficulty levels, and we quantify this sample rate and utility gain. And we compare ours with random sampling. Basically, the intermediate step is randomly perturbed from the original constraints. And we also compare with different language models. So in general, we find that our language model can achieve much higher success rate and the utility gain compared with other methods, both random sampling and other language models. So that tells us that at least on this synthetic data set, on some unseen problems, after the fine-tuning, after the reinforcement learning fine-tuning, the language model can roughly know how to map the unseen constraints to a new distribution that more likely to give us better utilities, lead to better intermediate steps. But this is actually a very challenging problem because it's much more beyond the naive formalization and program synthesis. So we can see that many language models cannot actually do this job, and some GPT models can not even give us some valid intermediate proposal. And one remark here is that we also need to pay attention to this valid intermediate step. So although in some cases we may find that the GPT-4o is very high, but actually the portion of the valid intermediate step is very low. So that means on those 2% of the valid proposals, they can achieve good performance. But out of all those 98% of the invalid proposals, they cannot do anything. So I personally think that this is an interesting result. So I think basically I think that this is a highly non-trivial problem that I think is even hard for human experts to quickly give some suggestions on proposing some good reasoning steps. But we can show that the language model can learn some implicit mappings from the original constraints to some intermediate steps. So I can give some examples how this solution look like. All right, I need to slow this video down because it's very fast. All right, so the two rows. First row is the naively solving this problem, basically no intermediate steps. And second row means that we will introduce the language model proposed intermediate step. And on the left is the system state. On the right side is the solution. So basically, on the left-hand side, you will see the chain of the system state along these temporal steps. And on the right side, you will see at different temporal steps how the language model choose different ways to control the problem. So here, this is a wave propagation problem. So that's why we show the external force applied to the system. And again, this colorful bars means the constraints is essentially we want to achieve. So here, in the first 0.1 seconds, the red vertical line means that before this 0.1 seconds, this system is solved by the reasoning step, the language model's proposal. But in the first row, there's no reasoning, so the language model just naively formalize the problem and directly solve the problem. So basically, the first 0.1 seconds, the behavior is different. And this first seconds, 0.1 second different behavior will lead to different behaviors afterwards. So after that, because after the 0.1 seconds, the system will locate at very different system state. So this different state will lead to different solutions after the 0.1 seconds. And then, so we see that different behaviors of two systems. And essentially, I didn't show the number here, but our solution will be better than the solution done by naively solving this problem. So I think due to time constraints, I won't go into details, but here is the end-to-end solution. So that means the code synthesis will be dependent on some noisy predicted LUs. So this ultimate RMSE will be the true RMSE that combine both the autoformalization and program synthesis. But still, most of the time, our model is better than other models. And also some end-to-end results for the reasoning part. So at the end, I just want to show some promising features for this direction. So you may ask one question that if it is necessary, always necessary to use language models to solve this problem. So one quick answer is that no, because essentially if the problem is already well defined and there's no noise inside the problem definition, then we can train some other very simple models to do this. But our proposal is that the core benefits of introducing language model in this problem is that we can achieve the human-centric and end-to-end automation of this control problem. So the human-centric means that we want the whole system to be resilient to some informal or noisy human language inputs. So this is the key motivation why we want to introduce the language model, because as long as our training data is very diverse, then the language model can robustly extract the constraints and the initial conditions from some informal and noisy human language. And it's always true that the original definition of problem always comes from the human. So human can make some noisy inputs. So that's key to make the system human-centric. And the end-to-end means that essentially we want to achieve a end-to-end system that takes from the problem from language inputs to the final system state control. And the automation means that we want to do some plannings and reasonings to achieve this control problem better beyond just naive execution. And so there are much more advanced problems that hopefully we can extend our solver to, such as Navier-Stokes or some transport equation that can model the traffic. All right, so that's the end of my talk. So thank you very much. I can take some questions.
Very much.
Thank you.
Questions?
So if you only use and constraints, and then you do have a convex problem. It becomes non-convex only with or, because the PDE is linear, the constraints are linear.
One more thing is that it will be convex if we only use and we further have these two different operators. So this F operators means that
the constraints only need to be satisfied one time during the during T1 and T2, this type of
So that's a fancy or.
yeah, another fancy one, yes. But if we always have and this
Right.
this and then it's it's a complex form, yes.
So I guess why, let me try to frame the question properly. So, looks like you're studying like this 6 seek problems, and you never test like sort of out of domain problems, and did you?
Yeah, so I think it depends how you define your OD generalization. So from all right, so if we only consider up to 3 constraints, I think first 2 bullet points are complete. So we really exhaustively iterate all possible combinations. And some principal OD distribution is that suppose we sample some hyperparameters out of our range. So that also
Right, so
definitely
I guess my question is really like, why do we want to, what's the motivation to do this? Is this the currently when people try to solve these PDEs? Is there a huge number of problems coming every day that we need to automate it? Or is it something like you're thinking, like, I'm using this as a toy problem to study this, but this gives us some possibility to generalize maybe into similar problems?
Yeah, I think that's the point. So definitely all the problem we consider are kind of toy, but we want to, the core idea is that we want to show both the possibility and the possible way that the language model can do not common sense reasoning. Common sense reasoning means that there are lots of NLP people that try to solve some daily life task, which is very different from these scientific problems. So we want to show that the language model can do this reasoning over scientific problems by a carefully designed training strategy. So definitely this problem are toy, but if we can,
so there are several parts. So if we improve this solver part to support, say, 2-dimensional or 3 spatial dimensions and more advanced PDEs, then I think the training of our language models doesn't have to be changed too much.
So I was trying to understand what are potential utility of this whole research, right? Who will get benefit from this? And from one hand, education definitely could benefit from this, right? And when you teach engineering students and STEM students that this can potentially you can generate like, I don't know, LLM based TAs that will
I mean,
help you teach your course. But
that's true.
Other than that, is there any other implication?
Yes. I think there are 2 implications. Suppose we can generalize this framework to more complicated PDEs. So first is that if there are only 2 or 3 constraints, human can still handle it. But if we have more and more constraints, just combining logically correctly combining these constraints will be very complicated. Human can, the more constraints we have, the more probability that human can make mistakes. So automatically formalize the constraints itself is already meaningful. It's very in practice that such as in building the air foyer or control the fluid dynamics, we may have lots of constraints. So formalizing the constraint itself is meaningful.
So you're saying the translation part is actually important?
Yeah, I think it's important.
This is actually a question from NK again. Is it not reasonable to assume that most people who need to solve PDE problems can write the tag code and they can directly, like maybe like he was suggesting, why wouldn't it be possible to just remove the autoformalization part and just focusing on the second?
So we cannot remove that part because we still need ways to formalize the constraint, right? That's always the need to. I mean, the human will write some informal constraints, and when human writes the problem, they may not consider the correct order, right? And also there are.
So you're saying that STL is actually not everybody who can solve PDE can actually use that tool.
People with background in the tech and STL can definitely write this logic, but no one can guarantee that human will not make mistakes if we have lots of constraints. So we want to, yeah, we want to reduce the human efforts and reduce the problem of errors when people need to deal with lots of constraints.
So that's actually related to my first question. Like
Mm.
in real world engineering practice
Mhm,
or use cases of these PDEs,
Mhm.
did you talk to people like, do they actually need to face their problem actually have many constraints in
Mhm, mhm.
reality or,
Mhm.
or
First, that's a good question. I didn't do that, but yeah, but
I don't
as
either.
yeah, I mean, it's a good suggestion. I think I should do that. Yeah.
Colleagues, mechanical engineering colleagues.
Right. That's a good suggestion. I think I need to do that. Yeah. Frankly speaking, I need to know if
From
I'm.
your experience.
Yeah, well, my consulting experience is the opposite of what you said, that plenty of people suggest PDE problems that have no idea how to solve them.
Okay.
So the translation,
But the other thing is, an interesting application area would be finance. So
Right.
there are plenty of people in finance trying to design
Mhm.
financial strategies, and there's lots of constraints.
That's true. Yeah. And another thing is that
Scholl's theory of finance
Mhm.
is PDE based.
Mhm.
So
Mhm.
it's
Yeah, that's true. So, but again, thanks for the question. I think I need to find that answer. Yeah, and another thing is that we want to and especially for some complicated problems, we want to help people to find better solutions. So that's another motivation. Yeah.
There is Ankit, apparently very interesting your talk.
Thank you.
Another question,
Mhm.
do we have any idea about the error rate of humans and LLMs on the constraint?
On the constraint of the formalization part.
Right.
Again,
You don't have,
we didn't ask
there yet.
yeah, we didn't ask a human to do the labor works.
Summer school and bring a bunch of students.
Yeah, perhaps, yeah. I apologize, we don't have that part, but it's definitely meaningful. I totally agree. Yeah. Actually, I think I need to write down these questions.
thing. They're driving on the wrong side. So is that Britain? You know where that picture's from? Or is it
Maybe
from British.
Sorry,
Hong Kong? Maybe they still drive on the wrong side of.
Yes.
sorry, it's just Google.
Okay.
Very cool. Very cool. Well, thanks, Muyang.
Thank you.
Thanks,
Thank you.
for the
I really love these questions. I really need to take some notes to memorize these questions. Yeah.